Thank you very much, and thank you for inviting me here this evening to talk to you all. So this evening I'm going to, this presentation is one which I originally gave back at the Vertical Lift conference in Bristol back in November, but I've taken out a lot of the deeply technical part of that and put some more introductory slides in at the beginning. So hopefully it's a bit less deeply technical and won't put too many members of the audience to sleep. I want to talk to you tonight about electric vertical takeoff and landing aircraft and some of the particular challenges that they're going to face when we come to try and operate them in an urban environment. And this is something which I don't necessarily think the industry's really grappled with yet, and that's hopefully that should come through in what I talk to you about this evening. First of all, though, I just quickly want to introduce Nova Systems, the company that I now work for and come from. This is the Nova Group. We're a global engineering professional services company. Various companies make up the Nova Systems Group. Formed in Australia about 20 years ago, and Nova Systems UK formed in the UK just over 5 years ago. And in fact, we have one of the founding members in the audience this evening. We've gradually expanded quite rapidly in the UK. Do various things, but our key DNA really lies in flight test and provision of flight test services. But we now cut into mission simulation, flight simulation, systems trials, aerospace design as well, and integrated test evaluation and acceptance planning. So quite a broad range company, but very much the focus was in test flying, and many of us in the company come from a test flying background, like myself. So what am I going to talk to you about tonight? Well, first of all, I'm going to talk to you about what the problem is with these electric vertical takeoff and landing aircraft and operating them in an urban environment. What's the problem now? I'll talk to you about the control systems, albeit at a very superficial level. And what are the technologies that might be used to overcome this problem? Some of the challenges with those technologies, and then some conclusions and about how the industry might like to take this forward. And then I'm not going to talk for very long because I'm keen to open it up to questions and discussions from the floor as soon as we can, really. So first of all, what is electric vertical takeoff and landing, or eVTOL aircraft? What are they? Well, it's a boom industry at the moment. There were certain technological enablers that came about really over the last 10 years or so. Some of it is to do with electric motor technology. A lot of it is to do with increased performance of batteries, and also some of it's to do with the increased performance of composite materials. And this has led to the ability to produce a new breed of aircraft. And there's examples there. The one at the top is an aircraft proposed by a company called Joby Aviation in California, and the one at the bottom is an aircraft developed by Lilium, who are a company based in Germany. These aircraft, because of developments in control systems technology and enabling technologies like GPS, reducing the size of inertial navigation systems, means that the aircraft can be potentially be automated very easily, and so you sometimes maybe hear them referred to as passenger carrying drones. The market for this is predicted to be absolutely enormous, and the ride-hailing company Uber have very much got behind this, and they've created something called the Uber Elevate Conference, which they run every year normally in California, and they're really trying to encourage manufacturers to build these aircraft so that they can start offering flying taxis as opposed to just taxis. A common theme with these eVTOL aircraft is that a lot of the companies who are developing them are funded by the Silicon Valley billionaires and the app billions. Joby Aviation is, and you've also got companies, sort of offshoots of Tesla are looking at this, and a lot of the other companies there. So although there are companies looking at these aircraft all around the globe, probably the sort of hub of development for these is in California. There are about 130 projects currently in development, of which generally the prediction is that about 90% of them are going to go bust, because it will be the first people to develop and then mass produce the electric flying taxi, they're the ones who are going to achieve market dominance. And you can see this real race developing, as I say, particularly amongst the American manufacturers, as to who's going to get that aircraft certified and built first. So it's the race is wide open at the moment. However, what are the problems likely to be? One of the key things is that these vehicles are going to be operated in an extremely challenging environment. And I'm not 100% sure yet that if people are sat in very sunny, generally very nice weather California, where actually once you're out of the main built-up areas, there are a lot of low-rise buildings, the space is quite open and there aren't a lot of other aircraft, then actually having these things flying from point to point, all GPS guided and automated, seems very realistic. I'm not sure an awful lot of these people have thought about how that's going to be when it's London and it's February and it's freezing and it's foggy. It's a very, very different situation then. So we're talking about operating them in highly congested terrain which changes quickly. You know, there are cranes, scaffolding, masts. Buildings can go up in a matter of days, if not weeks. They need to be able to operate in mist, fog, drizzle, rain, at night, and actually potentially in snow and freezing conditions. Because actually we're only really going to see an urban mobility revolution if these aircraft are exactly as reliable as the Uber you get on your smartphone or the black cab that you hail. They've got to be reliable, otherwise you'll return to the old adage of, you know, time to spare, go by air. It's also going to be very congested airspace. A lot of these aircraft have potentially quite high performance. Certainly the assumption seems to be that in an urban environment they'll be doing around about 150 miles an hour. So actually, if you've got them going both ways down a street between high-rise buildings, you're talking about a closing speed of 300 miles an hour. Now, although we have got precision navigation systems, what happens if the inertial navigation system fails? What happens if there's some GPS jamming? What happens if there's something which doesn't mean that you can absolutely guarantee that two of these aircraft are not going to hit each other head on? We're also talking about potentially quite high levels of turbulence here. If you think about sort of 40-mile-an-hour winds in the lee of the Shard or a very tall building, that's actually going to create an extremely turbulent flow. And certainly any helicopter pilots in the audience who've flown helicopters in mountainous conditions know that can be quite a bumpy ride. And it'll be no different for these aircraft as they're trying to land on top of a skyscraper or indeed just cruise past one. Looking slightly, rather than looking forwards now, looking back, actually a lot of these problems have already been looked at by the helicopter community for quite a long time. So you'll hear the phrase DVE, which means degraded visual environment, and that can mean anything. It can mean a sandstorm, it can mean a snowstorm, or it can mean fog. Anything where the pilot of an aircraft can't necessarily use the visual references to be able to fly that aircraft or to know where they are and what the orientation of the vehicle is. This problem got great prominence really during the military operations in Iraq and Afghanistan, where it was very, very dusty. And an awful lot of aircraft were damaged. Tragically, a lot of people lost their lives in these accidents, where helicopters were coming into land in a very dusty environment, and suddenly, as you get to kind of the last 25 or so feet, the dust just shoots over the top of you. You can't see anything out, can't even see the wheel on the aircraft. And it's extremely difficult to know which way is up. Particularly if you're then trying to do it at night and you're trying to do it without any form of light or low ambient light levels, so perhaps your night vision goggles don't work so well because you're obviously, for good military reasons, you're trying to do it when there isn't a moon up. We've also looked at unmanned air system operations in uncontrolled airspace. So this is when you're operating drones and you're trying to detect where other drones are. And there's been a lot of research that's gone into that. But the problem really is even older than that. It doesn't just date back over recent advances with drones or indeed the operating helicopters in a degraded visual environment. Operating aircraft close to the ground in bad visibility has been a problem really since man started to fly. We can go all the way back to accidents back into 1996, where there was an S-76, a tragic accident in the Mourne Mountains in Ireland. Coming forwards a bit, if we look at the accident with an Augusta 109 in London in 2013, that aircraft hit a crane on the side of a building, which wasn't necessarily marked on the map which the pilot had, and it was a case of a loss of situational awareness for the pilot in poor visibility below the safety altitude for the area. And I believe there are real parallels you can take from that accident into the electric VTOL operating conditions. Another interesting case study is the again tragically fatal accident of an AW139 in Norfolk in 2014. That was a really advanced aircraft. It had a forward-looking infrared system on it. It had a highly advanced autopilot system, twin pilot, and it took off in a situation of poor visibility from a field with a VIP owner in the back of the aircraft. As I say, in Norfolk in winter in poor visibility conditions, and the crew lost situational awareness, and the aircraft was flown straight into the ground just after takeoff, again tragically with the loss of everybody on board. Now the interesting thing to take away from that accident is the fact that the aircraft actually had all of the equipment on board to enable it to do that safely, and there were issues to do with regulatory approval to use that, to do with certification of some of the equipment, and also training of the crew to be able to use the type of sophisticated equipment that was on the aircraft. If we then bring that forward into the electric vertical takeoff and landing environment, if the first generation of these aircraft are going to be piloted, and generally the feeling across industry seems to be that they will be, because that's the only way that you'll be able to certify to fly them in controlled airspace, then all of these issues, all of the aggravating factors in some of these accidents, they're going to apply to the electric vertical takeoff and landing market as well. And again, that's something I'm not sure that the industry's really grasped yet. So what the helicopter community have done is try and break down the problem. And what they've tried to do is break it down into what they call the three legs of the stool. And this is, it's not a particularly complicated idea. It's about how you fly a rotorcraft or a vertical takeoff and landing aircraft close to the ground when you can't really see what's going on. What you need is something that tells you what the aircraft is doing, gives the pilot some kind of situational awareness, some kind of confidence that the aircraft is the right way up and in the right place. You need something for detecting the obstacles, detecting the crane, detecting the skyscraper, or detecting the person that's just driven across your landing zone, whatever it is. And you're going to need something that's going to help the pilot fly the aircraft. It can be a highly automated autopilot, which means that you can just literally take your hands off, or it might just be something that makes the aircraft easy enough to fly in that situation. But we've been doing this for a long time. We could go all the way back to the 1970s and a Sea King helicopter that you can see on the left there. Now, when they were operating in an anti-submarine warfare role out over the North Sea and the Greenland, Iceland, UK gap, and they were operating over water at night, they were operating in a degraded visual environment. And that aircraft, even though it's a long time ago now, it had all of those systems on board. It had a hover meter, just a simple Doppler hover meter that told the pilot whether the aircraft was drifting around. It had a radar altimeter to tell the pilot how high they were. It had a radar to make sure they weren't going to hit a ship or an oil rig. And it had an automatic flight control system which stabilised the aircraft, made the aircraft easier to fly. So it had all of those building blocks. All we've done in the time since then is make the problem harder and want to make it safer. So if we now move forward to now and actually say we want to go and do a landing in a confined area in a mountainous region of Afghanistan or wherever, we need to do that with a much greater degree of safety. We're having to bring in a whole new host of technologies here. And probably the most advanced aircraft, certainly that there's public knowledge about, is something like the HH60 Whiskey model, which is the picture of on the right there. So the very, very latest most developed version of the Black Hawk helicopter. That's got display night vision goggles, so the pilot is flying with night vision goggles, but which has information overlaid over the image. I mean, they're not particularly new. I was flying with DNVG 10 years ago now, but it's a huge bonus if you're flying at night, because it means you can keep your eyes out the cockpit and you've got awareness of what the aircraft is doing. It might have a terrain following radar. It might have an electro-optic system. It will certainly have night vision goggles. It might have an EGI, an embedded GPS INS, something so that the aircraft knows exactly where it is, probably to within less than its own length, and maybe even some other systems as well, things like a millimetric radar to detect obstacles. It was also like to have a digital automatic flight control system, possibly with what we would call advanced control laws. So the pilot will be able to take their hands off the aircraft completely, and it will just stay absolutely where it is. And it might be that the pilot, rather than controlling the way the aircraft flies, the pilot might actually just control the speed that it moves sideways or backwards, and make the piloting task much easier. So that's where we've got to. But how do we now solve the problem of these electric vertical takeoff and landing aircraft operating in a frozen and foggy London? Well, broadly speaking, the manufacturers who I've spoken to seem to think that what we're going to be able to do is just sanitize the airspace. We're going to be able to guarantee that that aircraft flying on that route, around that urban environment, around that city, is just, as long as the aircraft knows where it is, it's not going to hit anything. Now actually, that sounds like a great leap of faith, but to some extent we already do it. I mean, you are not allowed to go and erect a mobile phone mast at the runway threshold at Heathrow. There are regulations that will prevent you from doing that. But they require standards and regulation. They require enforcement. For example, enforcement of drone exclusion areas around airports. And they require cultural change as well. I think people would think that it is not a sensible or safe thing to do to go and start using a large crane near an airport. Actually, evidence would suggest there are maybe some people who need to be educated that it's not a good idea to fly a drone near an international airport. However, if that isn't going to provide your required level of safety, then you need to be able to detect something that's in the way. Now, it might be a crane, it might be a building, but actually it might just be a really big bird. Or it might be somebody who is just literally driving across the landing site. This is where the real technical challenge comes in and has yet to be overcome. Certainly, all of the technologies that have been used in the helicopter world for the degraded visual environment have yet to achieve this particular level. Now, if you take the smallest thing that can damage a rotorcraft, certainly a conventional helicopter, is something around about the size of about 4 millimeters size. So if you think about something like a telephone cable stretched between two buildings, something like that, that's the sort of thing which may not get cut by a rotor. It might wrap itself around it and stall the rotor. And actually, if you're approaching that telephone cable at 150 miles an hour, and you've got to guarantee that it reaches a certain level of safety, which is generally 10 to the minus 9 for the certification authorities, you're turning round to the sensor manufacturer and you're saying, right, I would like you to develop me a sensor which can detect anything larger than 4 millimeters when I'm flying towards it at 150 miles an hour in freezing fog, and you need to be able to guarantee to me that its probability of failure is going to be 10 to the minus 9. That's really, really hard, and I'm not aware of anybody who's achieved that yet. We're also going to need to be able to decide what's a false alarm. What's a false alarm, and what actually is somebody who swung the cable from their crane into the air taxi route or the air taxi airway. Maybe artificial intelligence is a way of doing this, but then that's actually very difficult to certify as well. If you turn around to the certification authorities and you say, don't worry, we can filter out all of the false alarm rates because we've got an AI algorithm. Okay, tell me what it does. Kind of does what it's learned. Okay, tricky. You can't absolutely guarantee that you're going to achieve that level of safety. So maybe we look at collision mitigation. Maybe we say, well, okay, well, at some stage, one of these flying taxis is going to hit something. So let's now look at, after the collision, how are we going to mitigate against that? Well, helicopters already do that. They have wire strike protection systems, wire cutters on them. They are very, very good. They're a significant benefit towards safety when you're flying in a low-level environment. But they're heavy. And also they need to be mounted on part of the aircraft that isn't going to break off if they hit the cable. So they have to be mounted on stressed structure, and that increases the weight again. What about crash-worthy seating and structures? Again, it's not new. It's been used in the rotorcraft world before, whether it's crumple zones on the bottom of a helicopter, or whether it's a crash-worthy seat that absorbs the energy of impact. Again, it may well work, but it's heavy. And finally, ballistic parachutes. That's an idea that's been presented for a number of these aircraft. In fact, it's already used in the light aviation world, such that if an aircraft gets into an irrecoverable spin, or perhaps some sort of stall scenario, then they can use a ballistic parachute. Again, out in uncontrolled airspace over rural land, probably fine. But actually, if you're walking along the street, are you going to be particularly happy about your 2-ton flying taxi coming down on a parachute? Again, interesting, and again, not something I think has really been considered. The sensor problem, as I alluded to in the last slide, I think is the greatest challenge. There are various systems you can use. There are passive systems, so systems that don't send out some form of electromagnetic radiation to detect the obstacles. There are infrared systems, there are image intensifier systems, there are even database systems and sort of see and remember systems. But the problem with database is they have to be absolutely up to date, and that then brings in a whole host of cost with it. You know, you've got to, as soon as that mobile phone mast goes up in that city, you've got to make sure that the flying taxi people know exactly where it is, and it would have to be done, you know, almost to the minute. Well, that's possible, and with network-enabled, wide area networks, that sort of stuff, it's possible, but it is going to drive the cost up. Or you can use active systems, so systems that actively detect obstacles. Microwave radars are quite successful, although less so in rain. Laser systems are quite good, though less so in dust. And they can be fixed, just staring ahead. They can be mounted in a turret, or they can be a staring array, so you've got sort of sensors all over the aircraft. But again, this is adding weight, and this is adding cost. There's some examples here of some obstacle sensors. The one at the top is from Elbit Systems, which is their Bright Night, and then there's a couple of other systems, one from Airbus Defence and Space, or now Hensoldt. But they're heavy, they're power hungry. Some of them work better in different situations than others. Some work well in dust, some work well in fog. You're not necessarily, so one sensor that works particularly well in freezing fog in London might not be the one you want in Dubai in a dust storm. In fact, I can tell you it certainly won't be. It's also quite difficult to benchmark against the human eye. If you're turning around to a certification authority and saying, right, we've got this sensor, it's fantastic, it detects obstacles, it's just as safe as the pilot. It's quite difficult to actually say how safe is the pilot. We're talking about a fresh pilot or a tired pilot? You know, a pilot who's got absolute ninja vision, or a pilot who just got through the medical by memorising the letters on the board as he would. No, that would never happen. Never happen. So what are the conclusions? I think first of all the industry needs to determine if sanitised airspace is going to provide the level of safety required under all the foreseeable conditions, emphasis on all of the foreseeable conditions. And if these first generations of aircraft are going to be piloted, which the suggestion is that they will be, then I think the community need to look back at what's happened in the helicopter world over the last 10, 20 years and make sure that they're not learning lessons all over again from them. And if the sanitised airspace isn't going to provide the solution, then we really need to start developing some sensors that are cheap, light, and don't use very much of your battery power. Because for these aircraft, the more battery power you use, the less far you're going to be able to go. So I think there's going to be a requirement for quite a bit more research and development into the sensors and also the algorithms that are going to process the collision avoidance. The industry is very much wants these aircraft to be, if they are going to be piloted, they don't want everybody to have to achieve a single pilot instrument flight rules commercial pilot's license. That's just too expensive. They need to be able to do some form of relatively short urban piloting course, whatever you want to call it, an urban vertical lift license. Now, the Federal Aviation Authority, the FAA, are already open to this idea. They're already talking about it, as long as it's as safe as anybody flying in a helicopter. So actually, if we're going to give people less training, and we're not talking about putting fully trained vertical lift pilots in there who've got, 100 hours night vision goggle flying experience in the front of these aircraft, well, actually then the obstacle processing and the assessment of the risk is going to need to be done by the sensors themselves. They're going to need just a big red warning, right, stop, I've detected something. They're not going to be able to make those judgment calls themselves that an experienced pilot might make, looking out for telegraph poles in the corner of a field or other things that you learn from hundreds and hundreds of hours of flying at low level. So that's the end of the presentation this evening. I'm very happy to take any questions or even open up discussion. Tell me I'm mistaken, whatever.